Let's have a look here. The following question is on rotation and simple harmonic motion. Let's take a look. A disk of mass capital M and radius capital R is pinned half of the way along its radius and held in a horizontal position as shown in figure 1. The rotational inertia of the disk about its center is half mr square. The disk is released at t equal to 0 seconds and falls to the vertical position as shown in figure 2. And it continues to rotate about the pin. Answer the following in terms of capital M, capital R, and G. Before we answer the question, let us understand that the axis of rotation, which was originally at the center, is moved by a distance of r by 2. This will help us in applying the parallel axis theorem. Part A tells us calculate the rotational inertia of the disk about the pin. So to answer this question, as stated before, we are going to use the parallel axis theorem, which tells us that the moment of inertia about the new axis is equal to the moment of inertia about the original axis or the center of mass plus the mass m multiplied by the square of the distance between the original axis and the new axis, which in this case is r by 2. So we have this substituted as half mr square plus capital M into r by 2 the whole square. Simplifying this, we get the moment of inertia I as exactly equal to half plus 1/4, which is 3/4 of mr square. Let's move on to part B. Part B asks us calculate the angular acceleration of the disk at t equal to 0. So at t equal to 0, we understand that gravity provides the torque about the pin, and this causes the disk to rotate about the pin. So we can also explain the same through a free body diagram. This is the pin. This is the origin. This is the distance r by 2 as mentioned before. And here we have F due to gravity, which is nothing but the weight acting. Here we have the torque, Ft, let's call it. So we can use Newton's second law of rotation, which is the rotational equivalent of resultant force. We have resultant torque tau is equal to about the pin is equal to I into alpha. So resultant torque we can substitute as mg, which is the weight, times the distance, which is r by 2. This will be equal to the moment of inertia found out in the previous part, I times alpha. When substituted and simplified, and we make alpha the subject of the equation, we get alpha as equal to 2 times g over 3 times capital R. Let's move on to part C of the question. Part C tells us calculate the angular velocity of the disk when it is in the vertical position shown in figure 2. So we understand that when it is in the vertical position as shown in figure 2, the gravitational potential energy that the body has is converted into rotational kinetic energy. And in the due course, the center of mass has fallen by half the distance to the radius. So we know that the gravitational potential energy E1 is equal to rotational kinetic energy E2. We will substitute gravitational potential energy as mgh, capital M times small g, and the height here is r by 2. This is equal to the rotational kinetic energy is given by the formula half I omega square, which is the rotational equivalent of translational kinetic energy. Half I omega square. The value of I is again substituted from part A, And when simplified, we get omega as equal to square root of 4 times g divided by 3r, all under a square root. Moving on to the last part. Now the disk is stopped and brought to rest in vertical position as shown in figure 2. It is given a slight disturbance to an angle theta naught. Calculate the angular frequency of oscillation. When it is slightly disturbed by giving an angle theta naught, it undergoes periodic oscillatory motion, and the nature of this periodic oscillatory motion will be such that the body will undergo simple harmonic motion, as the direction of acceleration will be proportional to and opposite in the direction of displacement. And for simple harmonic motion, we have acceleration A, which is the double differentiation of position d square x by dt square equal to minus omega square x, where omega is the angular frequency. The rotational equivalent of this will be d square theta by dt square is equal to minus omega square theta. So let's start with Newton's second law of rotation again. We have resultant torque tau is equal to I alpha. Resultant torque tau is equal to I into alpha. We go ahead with our substitutions. Torque tau will be substituted as minus m into g, capital M, into capital G into sine theta, since acceleration will act at an angle theta as shown here, minus m into g into sine theta into the distance r by 2, since torque is force into distance. This will be equal to I into alpha. I value is substituted again from part A, which is 3 by 4 mr square. So simplifying this, we get the expression to be equal to approximately minus 3g by, minus 2g by 3r theta is equal to minus or plus, d square theta by dt square. Equating this expression to the standard expression above, we get the value of omega square, or in fact omega, to be equal to square root of 2 times g divided by 3r. So here we have the final value of omega.